We all know that vibration monitoring is, the gold standard for checking up on these huge cable-stayed bridges.
Hmm, absolutely. You measure the hum, you calculate the tension.
Right, and you know if it's safe.
Mhm.
But there's this sort of ghost in the machine that engineers have been sidestepping for years. It's called damping.
The friction, if you ignore it, your numbers are off. And that can be dangerous.
And that's what we're digging into today. A 2026 study by Huintai, Pambao, and Wong Kong that really tackles this head-on.
Yeah, they basically argue that we're listening to the bridge with the wrong math. Our models are just too simple.
We're usually using the Euler-Bernoulli beam theory, right?
We are. And it works fine if you're talking about, say, a perfect steel wire in a lab.
But a bridge cable isn't that. It's this massive, thick, complex bundle.
That's the key distinction. Euler-Bernoulli theory assumes the cable is infinitely thin. It ignores the fact that when these thick cables vibrate, parts of them actually rotate slightly.
Sheer deformation, that kind of thing.
Exactly. All that gets missed. So these researchers switched to what's called the Rayleigh beam model.
Okay, so that model accounts for the thickness, the physical mass, and rotation.
It does, but that's only half the battle, because it's what's inside the cable that's the real problem.
Right, it's not just steel. It's wrapped in these polyethylene jackets and packed with grease or cement mortar. It's messy.
It's very messy. And all that stuff creates what we call a viscoelastic environment. Think of it like a shock absorber inside the cable itself.
So when it vibrates, all that grease and plastic creates internal friction. It dampens the vibration.
Exactly. And to model that, the study uses something called a fractional derivative Kelvin-Voigt model.
Okay, that's a mouthful. Let's break that down. Viscoelastic implies the material has a memory, right?
That's a great way to put it, yeah. If you stretch it, it doesn't snap back instantly like a perfect rubber band. There's a time delay while that energy gets dissipated through the grease.
So the math has to account for that time-dependent drag.
You're spot on, but here's the catch. You have this really sophisticated formula now, but to use it, you need to know the specific damping coefficient.
You need to know how sticky the grease is.
Uh-huh. And you can't exactly slice open a cable on the Fumai Bridge to find out.
So you've got a better formula, but you're missing a key variable to actually solve it.
Precisely. And this is where the study gets really clever and pivots from pure physics to statistics.
How so?
They used a hierarchical Bayesian model to essentially estimate it backwards, just from the vibration data they could see.
Ah, so it's like a detective story. You don't have all the evidence, so you look at the whole lineup of suspects to figure it out.
That's a perfect analogy. They looked at data from a whole family of cables, like C2102N and C2207N in the study.
And some of that data was probably noisy.
Incredibly noisy. The data from C2102N was apparently a mess, probably from traffic or wind. If you looked at it alone, your tension guess would be way off.
But the Bayesian approach pools the information.
Yes. It assumes the physical properties, the gunk factor, are probably similar across all the cables. It separates the real physics from just random sensor noise.
So it borrows strength from the group,
Mm-hmm.
and instead of one number for tension, you get a probability, a range.
Which is so much safer for monitoring. And they validated this. On the Hwamyung Bridge in Korea, they tuned the model and got the tension estimation error down to less than 4.71%.
That's a huge improvement.
A massive improvement in safety margin over the old methods. And they proved it wasn't just a simulation.
They took it to the Phu Mai Bridge in Vietnam.
A living, breathing bridge. They were able to map the real relationship between tension and all these damping coefficients right there in the field.
So it proves you don't always need expensive, disruptive physical tests to know if a bridge is safe. You just need math that's honest about the mess.
You know, engineering is often about making simplifying assumptions. But this study shows that as our structures get more complex, we can't afford to ignore the friction anymore.
We have to model the reality, grease and all.
We do.
It makes you wonder what other structural safety standards are built on perfect world math that might be due for a messy reality check.
That's the question that keeps a lot of researchers up at night.
Well, next time you cross a bridge, just be glad the math is getting better at listening. Thanks for joining us on this deep dive.